Thanks, it's really great to be here. And first of all, really ask questions, interrupt me if I say half of what I wanted to say. It will be perfect. Second, there are advantages and disadvantages of talking first. Advantages, you are done in an hour and you can enjoy your life with the rest. Disadvantage is that I have to start and there is a feeling, maybe not necessary, feelings that I have to give overall view of the field, which means that I probably will talk that little about the last things that I was doing. So this means that if you want to know what I'm thinking, how to get high TC, ask me questions later, and I will tell you about what I was doing in the last couple of years in this field. But I want to start with general discussions about how we can get superconductivity due to electron-electron interaction, which goes under umbrella superconductivity from repulsion. And as I said, since I'm the first, let me very quickly on this mnemonic remind you that superconductivity is the resistant states of interacting electrons. The first Nobel Prize out of, I guess, at least 3 given for superconductivity was given over 100 years ago to Camerling honors for this experiments on Mercury. And there's a lot of nice pictures associated with superconductivity, mostly related to levitation due to expansion of magnetic field by a superconductor. But if we generally ask a question, what we need for superconductivity, what is necessary ingredient for superconductivity, then you can look and say, look, if we drew the theory of metals, it of course tells you that resistivity should remain finite because it tells you that the current will be proportional to electric field with inverse proportionality constant, which is resistivity. And this is standard Ohm's law. And it's also important to realize that this is dissipative current, meaning that in order to sustain current, you need to constantly borrow energy from the source of electric field. But at the same time, this is a standard Ohm theory. At the same time, I guess from almost the beginning of quantum mechanics, it was known that if the system, by any reason, has a macroscopic condensate, which means that the ground state wave function of the whole system can be described by amplitude and a phase, then there is additional current associated with this gradient of the phase, which will not be accompanied by energy dissipation, and can exist already at zero electric field. So the question is how to get the state with macroscopic condensate, and of course the fact that there is a non-zero current at zero electric field means by this formula that resistivity should be equal to zero. So this is not an exact statement because of fluctuations which can destroy the coherent phase of the condensate, but still as a question of what is the minimum requirement, it's necessary to have a condensate, and then there is a good chance to get superconductivity. And for a bosons, what is condensate? Condensate means that there is a macroscopic number of particles in the same quantum mechanical state, so you describe the whole system by one wave function of the whole system without basically telling in which state individual particles are. And for bosons, we all know this is absolutely natural state of matter. It's called Bose-Einstein condensation, and this is because bosons like to cluster at low temperatures in macroscopic state with zero momentum. Nothing prevents them to do this. Fermions are fermions, and as we know, Pauli principle doesn't allow two fermions to exist in one quantum state if we include spin into consideration. So this is simple one-by-one problem, and the answer to how one can possibly get something out of fermions is somewhat obvious. That form a bound state of fermions. If two fermions with, say, spin 1/2 form a bound state, then the bound state has spin, total spin equal to either 0 or 1. In any case, it's integer spin, so the resulting particle is a boson. Bosons can condense, and this way you get superconductivity. So it looks like completely straightforward route to superconductivity, with only minor thing that we need somehow to pair fermions into a bound state. And to get this, there should be attraction between fermions. This is seems to be quite reasonable thing to guess. And this most known, I guess, Nobel Prize in physics for what is called BCS theory, which arguably is the best theory of the 20th century, has two parts. One part says that you can have arbitrary weak attraction, and it's already sufficient to produce a bound state of two fermions. And the reasoning is in any dimension. And the reasoning is that condensed matter, and this is the difference between condensed matter and high energy theory. The locus of low energy states is not at k equal to 0. It's at finite k called Fermi momentum. And the reasoning is that there's a finite density of fermions. They need to fill the states. And so every time when we need to take fluctuations and integrate over 3 components of momentum, 2 components of momentum, it doesn't matter, the result reduces to one-dimensional equation. So in fact, the problem reduces quantum mechanics to 1 plus 1 dimension, and 1 plus 1, 1 in space, 1 in time, and in 1 plus 1 dimension, you always get a bounce. So that was one part. Arbitrary weak interaction is sufficient. There is no threshold. Not the case, by the way, for phenomena which is called quantum critical phenomena, and superconductivity adds a quantum critical component. Second one is what causes that reaction. And in this respect, BCS theory is always associated, right or wrongly, because I think it's more genetic theory than this, with attraction due to exchange of foreign body of quantum lattice vibrations. There is various way to describe how to get attraction out of this, but short story is that electrons come in, creates deformation of the lattice, another electron after some time, this retardation, comes into the same area, feels retardation of the lattice, deformation of the lattice, and due to this deformation, the 2 electrons effectively attract each other. Which is absolutely true. And the question that was somehow put under the rug is, yes, there is attraction due to phonons, there is also repulsion due to electron-electron interaction. It was somehow believed for years that at the end of the day, you can forget about electron-electron interaction to first approximation, and electron-phonon interaction is sufficient to give you superconductivity. Which is true when there is a big separation of the scale, for example, when Fermi energy is much larger than the biofrequency. Interestingly enough, it was done in '57, rewind forward to 2019, this year, people are now reevaluating the story for the case when Fermi energy and the biofrequency are of the same order, and it's not entirely clear whether this mechanism gives rise to superconductivity in the case, because of Coulomb repulsion, which acts against electron-phonon pairing. So the total story may be a little bit more complex than originally thought. But the title of our school is different. It's superconductivity with electron interactions. So let me switch from phonons to something different. And very quickly, the new era, which promoted all research in different fields, started in 1987, 86, although some people were talking about superconductivity due to electron-electron interaction earlier. With the advent of cuprates, then iron-based superconductivity in iron-based material came in with a large number of Nature and Science papers. And the question is, what we're talking about? Are we talking about really new because of high temperature superconductivity? Well, partly the answer is no. This is one example, and GB2 is definitely phonon superconductor with TC of 40 Kelvin. The record highest superconductivity temperature under pressure is also for phonon-mediated superconductors. So why we're talking about electronic scenarios? And at this stage, the answer will depend on whom you ask. My point is that in a number of materials, it is not entirely guaranteed, but there are good arguments that by one reason or another, electron-phonon interaction will not work. Either by pairing symmetry, electron-phonon interaction just will not give you pairing symmetry that is observed in the experiments, or by purely numerical reasons. This is one example that I like to cite, that for people who promote actually electron-phonon interaction, they calculated TC for iron peptides and found that even without this negative effect of electron-electron interaction, you get roughly Kelvin. You can make it larger by 5 Kelvin, but not 60 Kelvin. That is highest temperature seen in experiments. So if by purely reasons of looking at symmetry, at the numbers, electron-phonon interaction seems to be incapable, then this brings us to the subject of this school, that what is left? Then there is not much left. it should be electron-electron interaction, which is repulsive interaction. So then the question one can ask as a zero-order question is that how one can get bound state of two fermions out of nominally repulsive interaction. And this brings me the issue how to get superconductivity out of repulsion.
So what was the card group?
This one?
Yes.
Well, obviously, water and wine. This is old story. And the story began in the 60s without great fanfare. But this story came from two different sources. As often happens, two groups. At that time, you know, there was a wall between two parts of Europe and one country and the rest of the world. And so two groups were working essentially independent of each other, but obtained pretty much the same result in the same year. This is all about isotropic system because people were thinking about helium at that time. And they made three statements. All three are relevant. Statement number one, that fermions can pair into bound state with non-zero angular momentum. When we talk about phonon-mediated superconductivity, we are normally talking about pairing into a state with angular momentum equal to zero, which is called S-wave pairing. They were the first to make a statement that not necessary, you can also pair into state with different angular momentum. Second statement was much more powerful. That if you look at the pairing problem decouples between harmonics with different angular momentum m, which substantially loses the restrictions on the interaction. It doesn't have to be attractive at all. So general interaction doesn't have to be attractive. It's sufficient to have attraction for just one value of angular momentum m. It can be, interaction can be repulsive in all other momentum. If it's attractive for one value of m, it's sufficient to get superconductivity because pairing in channel with angular momentum, say 10, doesn't know anything about pairing in channels with all other momentum. This was really very powerful statement made by both groups. And third one is essentially most relevant to what I'm going to talk about. That if you ask, let's take formal limit, really formal limit of large angular momentum, and ask the question, where does the interaction come from? Well, the answer is that interaction comes from large distances. The larger is angular momentum, the larger are the distances between fermions which contribute to this interaction, to a component of interaction with angular momentum. Why is this relevant? Because if you take screen Coulomb interaction, and just open textbooks on screen Coulomb interaction, you find out that besides the standard story with Coulomb interaction transforms into Yukawa potentials, this irregular screening, there is something else. It's called Friedel oscillations. That at large distances, screen Coulomb interaction necessarily oscillates. And so in oscillations which are related to robustness of the Fermi surface, this go normally as in 3 dimensions as cosine 2 kfr over r cubed, and they are known as Friedel oscillations. And if you look at this, you can say, well, this means that screen interaction can occasionally be overscreened. In these regions, interaction changes sign and becomes attractive. And then you ask the question, is it enough for superconductivity? Is it enough to have occasional overscreening of the interaction? Which brings me to the story with the name of Kohn and Luttinger, who looked at this theoretically, carefully, in 1965, long time ago. And they really, very rigorously, it looks like perturbation theory, it's not, it's rigorous theory. They rigorously asked what happens if you take arbitrary regularly screened interaction, U of r, and add on top of this effect of Friedel oscillations. And they found exactly that at least for odd large value of m, you may ask what it all means, but theory, you necessarily have attraction. And this was wonderful because this was the first real example of superconductivity from repulsion. You start with electron-electron interaction, which is totally repulsive. You screen this electron-electron interaction, and because the screening introduces this oscillating component, there is occasional overscreening, which on average does very little, but if you zoom on particular angular momenta, you find that this overscreening wins, and you get effective pairing, attractive interaction. This was considered as joke at that time because there was a story associated with that paper. They were too honest to give estimate for TC and get TC of about 10 to minus 20 Kelvin, which was 0 by all accounts. It turns out later that they were applying the results to angular momentum L equal to 2, while if you take their results and apply to angular momentum L equal to 1, you will get 10 to minus 3 Kelvin, which would be similar to temperature, to TC for superfluidity in helium 3.
Can you comment on the odd n? Can you comment why odd n?
It's, in fact, this is the word definitely here. Let me start using this. The word definitely here. For odd m, so what really this story is that out of interaction u of q, which is arbitrary function of q for generic screening interaction, what contributes to this Friedel oscillation, or to the component which are due to Friedel oscillation, are components u of 0 and u of 2k. Now, why large m? Why is this important? Because if you take regular screened interaction, some analytic function u of q, and calculate what will be partial component with large angular momentum m, you get partial component which is exponent e to minus m. So for large m, it's exponentially small. Friedel oscillations give you non-analyticity in the function u of q. It's logarithmical non-analyticity, but still non-analyticity. That's a term which in Fourier transform give you cosine 2k of r divided by r cubed. Because of non-analyticity, contribution from this Friedel oscillation decay as 1 over L to 4th power, which is of course much larger than any exponential function. Then you ask, what is the coefficient in front of this 1 over L to 4th power? And you find that it only has components u of 0 and u of 2k. Only forward scattering and back scattering, nothing else. And then what they found is that for odd value of m, the coefficient is minus full square. So it was guaranteed to be positive. For even values of m, it can be positive, can be negative, so there was no theorem. Which brings me to a more simple version of the same story. That if you go to times, present times, when Hubbard model is the model for consideration, and consider what happens if you don't do what Kohn-Luttinger did, but said, okay, let me assume that regular screening is so strong that I consider only interaction when two particles contact each other and 0 otherwise, which is Hubbard model. Then you find out that to first order in this interaction, there is a repulsion in S-wave channel, Hubbard model. U is positive, so you have strong repulsion in S-wave channel. And there is 0 in all other channels. If you go to second order and you start doing Kohn-Luttinger type diagrams, not rigorous calculations, but just second order diagrams, you find out that for all values of L, so for all values of M not equal to 0, you get attractive interaction. So in this respect, attraction is for even L, for odd L. And then you ask the question, what is the largest? It turns out for P wave. So in this respect, the answer to this problem for the Hubbard model is very simple. If you have attraction, you get S-wave superconductivity. Electron phonon interaction is the way to get it. Or you take negative U Hubbard model. If you have repulsion, you get P-wave superconductivity for isotropic interaction. Temperatures differ, of course, in the magnitude, but nevertheless. So, but that was a wonderful story of physics of 60s, 70s of last century. The question is, what happens if you consider real lattice systems? So first statement is in some sense negative. For real lattice systems, there is no theorem that you ought to have superconductivity. For isotropic system, it was really a theorem. So in principle, lattice system can remain normal, non-superconducting down to 0 temperature. Nevertheless, it turns out that some elements of this Kohn-Luttinger treatment can be applied to lattice systems, and I think it's quite useful to apply them to lattice systems to see what we see. And by element of Kohn-Luttinger physics, I mean this, that if you talk about pairing interaction, you don't take your Hubbard U as the interaction. You dress it up by fluctuations in non-superconducting channels. Because Kohn-Luttinger physics is you take pairing interaction and dress it up by stuff that gives rise to screening of Coulomb interaction, which are corrections in the particle Hall chain. If you apply the same reasoning, then you have to include that screening or that renormalization into consideration and deal with effective interaction, which of course is a function, become function of momentum transfer, then with the pair interaction. And let's see how it works for particular cases. Again, my talk is the first in line, so I'll give you two simple examples. A little bit oversimplified, but still I think useful. So cuprates, the most spoiled field in condensed matter physics. What we know from phase diagrams that it's rather complex. We have antiferromagnet close to half filling, we have superconductivity under both hole and electron dotting, and we have a lot of stuff, including the gap, going in between. But in the simplest way, if you take overdoped cuprates, they are A metals, B they have large Fermi surface. And this is known from a number of experiments I just cited to them, very much important. Let's do Kohn-Luttinger type reasoning, very simple reasoning. We don't have angular momentum, we have lattice. So let me do it in a different way. What I will do is this. I will say, look, let me assume that dimensionless coupling constant that we deal with is the interaction times density of states, and just looking at this Fermi surface, I can ask where the density of state is the largest as a corners. Because if these points merge, density of states will diverge. They don't merge, but density of states is still enhancing. So if I just take corners only, and this is of course huge approximation, and ask what can I write as the interaction? Well, there's the interaction within a patch, I call it G1. There's interaction between patches, I call it G2. Let me take the simplest model with only two interactions and ask how many pairing channels are in this model. Two. Two couplings, two pairing channels. In fact, for a lattice system, I have 4 one-dimensional representations, but for 2 of them, you need to go beyond page modeling. So I have 2 couplings, and they are easily expressed in terms of these G's. Convention is such that lambda should be negative, and then you have attraction. Negative lambda means attraction. G is positive. And so you obviously see that for one channel, there is a huge positive interaction. This is repulsion. But like in the Hubbard model for isotropic system, if you look at another channel, and you take originally Hubbard model when interaction G1 and G2 are the same, you get in the second channel 0. So then it opens up a possibility, let me go, this is what I already said. This opens up a possibility to go to second order and ask a question. You start with 0, what you get, positive or negative when you renormalize. Just like in Kohn-Luttinger stuff, it was the same story. For the case of Hubbard interaction, you started with 0 for all channels except for S wave. You include renormalization from particle Hall channel, and you get attraction. Here is the same story. You include the same diagram for renormalization. I just wrote 1 because all others actually for this particular case cancel out. And you find out, and we'll discuss the reason in few slides, that the interaction between patches becomes larger than the interaction within patch. Notice this one. You need lambda negative for pairing. If this guy G2, interaction between patches, becomes larger than G1, you get this lambda negative. So you get attraction. So in this simple reasoning, you get the same story. You normalize interaction by just lowest order corrections from particle Hall channel, and you get pairing interaction in one particular channel attraction. Which channel is this? Well, it's not difficult to figure out that if you have interaction which is G1 minus G2, and you ask what are the values of the order parameters in page 2 and page 1, they change sign. For other channel, you will get the same sign that would be negative. Simple as. So you look at this, add to this that we're talking about spin singlet superconductivity, and so the gap in minus k, or order parameter at minus k, is the same as order parameter in k, and you necessarily find that your order parameter should change sign in every corner and every quarter, of the Fermi surface, which obviously means that it's V wave. So to get D wave, you just do second order perturbation theory. And you get D wave pairing for Fermi surface like in cuprates. And of course, this is only one part of the story. There are a number of interesting phenomena in the cuprates. But if you only ask a question from the point of view of superconductivity, all the phenomena basically tells you how TC goes down upon approaching half field. If you want to ask what causes the pairing, you can possibly go outside of all interesting ranges and consider either strong electron doping, either strong hole doping or strong electron doping, where the kind of reasoning that I described to you is applicable. And again, we'll go a little bit over it in the next few slides. But let me show you a second example, and before you'll be completely bored with all these examples, I will move on. Neckties. Zoo of electronic states, absolutely. But if you focus on what happens close to zero, you find out, I borrowed this slide from York's paper, these are multi-band systems with hole pockets, with electron pockets, and some of us had fun for the last 10 years working with all orbital physics, spin physics of this Kohn electron pockets. But if you just say, okay, let me do something extremely simple. I have electron pockets and I have hole pockets, which what means what? I have regions where dispersion is conventional, means that dispersion goes up and stays close to bottom R field, this is electron dispersion, or dispersion of opposite sign goes down and stays close to the top R all field. This is what hole pocket or hole dispersion. So if you take this and say, well, I have one pocket in the middle, one pocket on the corner, this of all the 4 points are equivalent, so it's just really one pocket. Then you can ask yourself, okay, say, well, what if I do exactly the same stuff? Only instead of patch, I now use the word pocket. So I have again interaction within one pocket, I have interaction between pockets, I call them the same way G1 and G2, and I do exactly the same reasoning as for cuprates. Again, two channels, two coupling constants, I need negative lambda for superconductivity. I go to Hubbard model, same story. One interaction is zero, another is repulsive. I do second order perturbation theory, and I get the same result. That interaction between pockets now becomes larger than interaction within pocket. So I ask the question what it means. It means that there is again sign change of the order parameter, but now between pockets. If I go along one pocket, the order parameter doesn't change sign. How I determine symmetry of the pairing state. I go along the Fermi surface that encounters zero and ask zero in momentum space and ask how many times the wave function changes sign. If it doesn't change sign, I call it S wave. So by this count, it's S wave. But because it changes sign between two different pockets, it has the name S plus minus, meaning that there are two different signs of S wave on two guys. And this again comes out instantly. You don't need to do anything besides 5 minutes of calculating of one diagram. You can look at experiments. There are many, and a number of people who did experiments are here. But just in a very quick ratio, it turns out that, already I don't know what it is, starting from very early experiments and then going to more recent experiments, you do find that you go along a pocket, whole pocket, and your gap doesn't change sign. It can have accidental zeros, but it's a different story. Which means that it's S wave. And you can also ask, is there any evidence that the gap changes sign between two pockets? Well, there's some evidence. Because if you ask theorists how to distinguish between conventional S and S plus minus, then they'll tell you, yeah, well, do neutron resonance, and because there is a sign change of the gap, you will have a peak at momentum that separates whole electron pockets, which happen to be pi-pi. So this is theory picture. This experiment, they clearly see there is a peak at momentum pi-pi at some finite frequency, which is totally consistent with this picture. So this is one of the evidence. There's other evidence that the gap really changes sign between two pockets. Let me stop here and say that was really order zero introduction. The whole story is wonderful, easy, and it's too good to be true. And first of all, it's too good to be true. because I cheated you in one particular aspect. I said, let's start with the Hubbard model. And yes, if we start with the Hubbard model, we start with the situation when there is one channel in lattice systems, at least one channel in lattice system, when the interaction is 0. And then you can start from 0 and say, well, I calculate corrections, they can be positive, they can be negative, but there's a clear way to get attractive interaction because there is nothing to overcome. Now, if I take survey and ask everyone here, you take screen Coulomb interaction, generally. Is it larger for small momentum transfer or for large momentum transfer? Well, you start with the interaction which is 1 over q, or 1 over q squared. And of course, interaction at small momentum transfer, even screened interaction, will of course be larger than interaction with large momentum transfer. So then we actually, if we look at the actual story, we always start with the situation when this lambda is positive. And then the question is, well, what I described to you before is perturbation theory. Then we have a more difficult problem, because we start with repulsive interaction. And we ask the question, how can corrections overshoot this repulsive interaction and convert repulsion into attraction? This you cannot do by just saying, well, I do weak coupling, second order perturbation theory, because then you will get nothing. And this is what most of us are doing. Some of you who remember movies of some years back remember from where it's taken. And there are 3 main theoretical approaches. And I will say here about one, few words about the others, and then a little bit, a few words about the second one. One is basically to abandon everything, what I told you before. Abandon the very idea that you deal with metal and with large Fermi surface and with sort of weak interaction between fermions, and to start with mode physics. Namely, to claim that in order to understand superconductivity, localization of electrons due to strong interaction has to be taken into consideration. This approach is generally called doping of mode insulator. It has a lot of merit, but let me skip this because otherwise I'll just have 1 hour, actually half an hour left, to talk about everything else. There is a second approach. Second approach that attracted attention from both high condensed matter and high energy people is to do this. Not abandon the idea that we deal with itinerant fermions, but abandon perturbation theory and somehow assume that we are close to some kind of density wave instability in the system. Which means that we cannot take a regional interaction, we need to take interaction mediated by collective modes which are solved because the system is close to particular instability. This approach generally means you deal with effective, not with the original fermion interaction, but with effective model where interaction between electrons and collective bosons. And this all goes under umbrella of superconductivity near a particular quantum critical point into density wave instability, out of which spin density wave is probably the most studied set. But people also study charge density wave. So what is this? I use the word spin fluctuation scenario. In some cases, I could easily replace it by charge fluctuation scenario. The story will be the same. This is not something new, something orthogonal to Kohn-Luttinger approach. No, it is the same approach. But Kohn-Luttinger, original Kohn-Luttinger approach, is essentially take second order diagram. Renormalize interaction, renormalize pairing interaction due to other channels, but do it at second order. Kohn-Luttinger did it rigorously because there was no non-analyticity. In latest system, you just do it as second order perturbations. Going back to cuprates, remember the story. The story is that we started with the case when G1 and G2 were the same, and we obtained that G2 becomes larger than G1. Now I want to consider what happens if originally G1 was larger than G2. But that story, Kohn-Luttinger story, basically tells you that this interaction gets larger than this one. If you look carefully where it comes from, why it becomes larger, then remember when we talk about particle Hall channel, we have to separate between 2 subcomponents of particle Hall channel. One is called charge component, another is called spin component. Simply because interaction can be split into charge and spin part if you deal with physical anti-symmetrized interaction. And if you look through the magnifying glass, you will find that the enhancement of this guy, the one that we need for superconductivity, come from fluctuation in the spin part of the interaction for repulsive G, etc. So then the idea of spin, original idea of spin fluctuation approach was to, well, if it's the case, why don't we go beyond second order and just sum up bubble series of diagrams like we do in RPA for screening of electron-electron interaction. And then effectively, if we do this, we end up with interaction between two fermions mediated by the sum of renormalization in the particle Hall channel, which can be equally phrased as mediated by collective excitations in the spin channel, which are spin fluctuations. So in this respect, spin fluctuation scenario is Kohn-Luttinger taken to infinite order. You don't have justification for this. You just do it or postulate it phenomenologically one way or another. There's one part of the game which you overcome because you want to overcome. You postulate attraction. You postulate that this guy is larger than this one simply because you want it to be like this. You sum up a particular set of diagrams which are guaranteed to you that this will happen. Nobody tells you that this is the right thing to do. But nevertheless, if you do it, you get it. But you have to pay a price. And the price you have to pay is that if you do this, you don't no longer assume that interaction is weak. And if interaction is not weak, then you need to think, what is the effect of the same interaction on fermions? And it turns out that you no longer can talk about fermions as being almost free quasiparticles. The same interactions that give rise to strong attraction between these two guys also tend to destroy fermionic coherence. And this goes under the wording non-Fermi liquid physics in the system with strong interaction. And then the whole story, the main story about superconductivity near any density wave instability is a fight between two opposite effects. On one hand, by hand, you just said, let's assume that interaction is attractive because we want it to be attractive. But again, then the same interaction gives rise to non-Fermi liquid physics. And two phenomena fight with each other. How they fight with each other? Very simple. Strong self-energy makes fermions incoherent. And if you go back and say, well, let me go back to BCS. Remember I told you that BCS give you attraction for arbitrary weak interaction. That was true for Fermi liquid fermions. If you take fermions which have non-Fermi liquid self-energy, which means that omega to some power smaller than 1, then you don't get Cooper logarithm. And you don't get instant superconductivity for arbitrary weak attractive interaction. You need to overshoot, you need to make interaction larger than threshold. You may say, well, I deal with strong interaction, but the threshold is also large. So it's a question about balance. On the other hand, if superconductivity wins, it immediately wants to make system Fermi liquid. Why? Because it gets low energy excitations. It may leave point nodes, but still overall it gets excitations. And if you recalculate fermionic self-energy in a superconducting state, you always get Fermi liquid. So then non-Fermi liquid physics will go away. So this is what mostly I'm doing. And again, if you have questions about this, I'll be more than happy to discuss detail. Jörg did wonderful work on SYK model, which reduces to pretty much the same. So we're all doing pretty much the same physics associated with wonderful field theory when you have competition between non-Fermi liquid physics and strong pairing interaction. I want to spend the remaining 15 minutes of my talk talking about the third approach. The third approach was also proposed by quite a number of people in various contexts. And this approach is try to stay with more or less rigorous theory. In this respect, try to stay with weak coupling. You can say, boo, this weak coupling approach, it's old-fashioned physics, we don't need it. But there is a caveat with this. There is a possibility to extend weak coupling analysis to infinite order. And to do this, you need to find something that multiplies weak coupling by a large number in a controllable way. And these are special logarithms which appear in actually every problem that people study, particularly iron-based. And this goes under the name renormalization-group approach. So let me say a few words about RG approach, because I think RG in some sense will be an intelligent way to see how tendency towards spin density wave actually promotes superconductivity. I already said that G2 comes from spin channel. Now we'll see it explicitly. So there are a number of people, the list is not complete, of course, working on various aspects on it. Sometimes it's called analytical parquet RG, numerical functional RG. So there's a number of approaches which so far give you exactly the same results. I don't know about any example where there is a difference between numerical functional RG and analytical parquet RG. Consider pnictide as an example, only as an example. Remember, we had two couplings, we need one for superconductivity, and then you ask the question, what are these couplings? So far, I was essentially doing BCS-like calculations. So I assume that when we have attractive interaction, great, we have superconductivity, which means I play with Cooper logarithms. Cooper logarithm exists only at energies well below Fermi energy. And so what we really need is to know the values of these two couplings at energies below Fermi energy. In iron-based system, Fermi energy, well, in some sense, in some systems, it's 5 MeV, but on average, it's 50, between 50 and 100 MeV. Bandwidths at which these couplings are defined is few electron volts. Again, we can argue what are exact number because of dual states, but definitely larger scale. So the question is, you start with couplings here. You need couplings here. How they evolve between these two regions. And this is what RG tells you. And coupling flow because of renormalizations in both particle-particle and particle-hole channel. And then I say, well, suppose the couplings is weak, then generally I expect that what we have here should be very similar to what we have here. But it's not. And the reasoning being that there are two reasons for flow which is just not simply small correction to coupling. One is that we have particle-particle channel. And then we say, well, particle-particle channel has Cooper logarithm, but we are above Fermi energy. We don't have Cooper logarithm. Do we have logarithm? Yes. And this is wonderful physics of 2 dimensions. That if you just consider free fermions with 2 dimensions, when you just consider zero density fermions in 2 dimensions with chemical potential is equal to 0, dispersion is simply k squared over 2m, then you get logarithmical renormalization simply because it's 2-dimensional case. It's not Cooper logarithm. Mockett was working on this starting from, I guess, 1990 something. And we have logarithm in a particle hole channel. And this is specific of iron-based. Every time we have one dispersion goes up and another dispersion, one dispersion goes down, another dispersion goes up. If you calculate particle hole bubble and momenta between this momenta between these two Fermi surfaces, you get log because energy. You don't need nesting. One energy can be 20 times larger than the other. What's important is that one is negative, one is positive. You get logarithmical physics. So you get logarithmical renormalizations. And we say, well, this means that I have to deal with something that is unpleasant because there are logarithms and I need to do something. But logarithm actually is a blessing. Blessing because you can go beyond perturbations. And the easiest example how you go beyond perturbation theory with logarithm is BCS theory. Because remember what you do in BCS. Your coupling is weak. But you know that when you renormalize your coupling in a particle-particle channel, this is now Cooper logarithm. You get coupling, next term will be coupling squared times logarithm. And you neglect regular G squared terms. You only include term G squared times logarithm. To next level, you include term G cubed times log squared, and for example, neglect term G cubed times log. So every time you include higher order of interaction and higher order of logarithm. And there is a way to do this. You can calculate leading terms. It's much more difficult to calculate sub-leading term, but the leading term are easily calculatable. And if you sum over all these terms, you get the famous BCS result. That there is some scale, exponentially small scale, called it temperature or energy, when the effective interaction blows up. which means system becomes unstable towards superconductivity. And you can do it like this. This is old-fashioned school of doing this. There is a little bit more modern way to do exactly the same. You write RG equation, meaning that you write equation on the running coupling constant, which depends on running energy. Equation is like this. You solve this equation, you get exactly this. So in this respect, you can say, well, I write RG equation as a way to sum up logarithmical diagrams. Or you can do it other way. You can say that instead of summing up complex logarithmical diagrams, I just write down RG equation. Anyway, this is equivalent procedure. Great. Then you can do a little more than just perturbation theory. Perturbation theory will stop here, at this level. But when you sum the whole series, you get instability. And this is much more than just doing perturbation theory. So in our case, there are two channels, particle-hole and particle-particle. Both are logarithmical. So it's a little bit more complex, but still doable. And all we have to do is to apply the same reasoning and see how coupling flow between energy being of order of bandwidth and energy at which we start our Cooper problem, which is Fermi energy. So how to do it? Well, you introduce all possible interaction between fermions. These two guys were already familiar to you. There's intra-pocket repulsion, there's inter-pocket repulsion, and remember, I want to start with the case when G1 is larger than G2. I want to make our life difficult. We start with repulsive interaction. We introduce two other interactions. We introduce forward and back scattering between pockets. These are interactions in the particle-hole channel. This is the ones that give you density wave, either charge density wave or spin density wave. And then you write down coupled RG equations. Let me not discuss how to derive them, but they're derived in a pretty standard way, although it requires a little bit of work to derive these two equations. Now, we need to solve these equations and see what is the flow. If I forget about these two, these are two couplings in the particle-hole channel. If I only focus on these two and neglect all particle-hole channel, then I will not convert water into wine. I will start with repulsive interaction, I will continue with repulsive interaction, and repulsive interaction will just get weaker and weaker when I go to lots of smaller and smaller energies. This is known effect. There is no way, like, working with only one channel to change the sign of interaction. But there is a coupling between these two parts and these two parts. And if I solve these equations, and in fact, if you plot them in Mathematica will give you the answer in a second, what you find is this. The system self-generates attraction, meaning I start the process with repulsive G1 larger than G2. So this is repulsive interaction. I run these equations, and what I get is that one interaction goes down, another interaction goes up. It's interesting. The system self-generates a scale below which means larger values of this logarithm. Smaller is energy, larger is logarithm. Here the interaction becomes attractive. It's a wonderful story which happens in all problems, including graphene, where you get D plus ID because of this. And this is nothing but enhancement of Kohn-Luttinger effect in a controllable way. This is controllable approach. You still assume that all non-logarithmical terms are weak, but logarithmical terms you include explicitly, and this is what you get. And the physics is interesting. You can ask, what happens here? Why? Because the system, why this G2 goes up and G1 goes down? Because interaction between pockets, or patches, whatever, is enhanced by interaction that grows up by itself. And that interaction will give you spin density wave. So if you look at this, you find exactly what happens. That as the system tends to develop spin density wave and stability, it also tends to convert repulsive interaction into attraction, which is another way to say that at the end of the day, spin fluctuations promote superconductivity. Very good. I'm doing exactly. Let's move a little bit further. Let's look at the real story. So far that was a toy model of one hole, one electron pocket. I didn't touch orbital content of the pockets, etc. If you look at more real story, it's multi-orbital model for iron-based. As I said, there's a zoo of states. And if you focus on low energy part, you have you have hole pockets, you have electron pockets. They're made out of 3 orbitals. So you ask the question, how many couplets you need to include? Well, the number is 44. So you have 44 different couplings, you have 44 RG equations. This is nice thing to tell from the podium. Yeah, guys, we did fantastic work for 44 couplings. And we really wrote 44 analytical RG equations, but I'm cheating a little bit here, because out of this 44, you immediately find out that a pretty large number of 30-something can be eliminated because the corresponding coupling flow to 0. So it's not really that difficult as it looks, but it's 44 couplings anyway. But the end of the story is exactly the same as I told you in a simple case. Spin fluctuation promotes superconductivity. There is, however, one more interesting part of the story. It turns out that if you include orbital content, spin fluctuations promote 2 types of interactions. They promote superconductivity, and also they promote interaction that leads to orbital order. There are 2 channels. One is superconducting channel, S plus minus channel. Another is orbital channel. Both are initially repulsive. And as the system tends to develop spin density wave, it basically changes sign of interaction in both channels by the same reasons. Then you may ask the question, what is the leading instability of the system? What happens? By the way, the question can be put this way. Why not spin density wave? Why we are talking about superconductivity? System tends to develop spin density wave. So what comes first? And this is where RG is pretty good. Because RG treats all channels equally. It doesn't tell you this channel is dominant one and this is not. Contrary to effective electron boson, Fermat boson model, which tells you, let's assume that one interaction is the elephant in the room. Either spin density wave or charge density wave, and let's see what the effect of this interaction will be. Here we don't do anything, we just start with all possible candidates. They are all combination of this G1, G2, G4, G44, and then ask which one will finish first. And this is nice analogy, but the real story is that you start with a situation when you have only spin density wave interaction effectively attractive. Remember, in order to get stoner instability, you need repulsive interaction between particles. Stoner magnetism comes from repulsion. So you have repulsive interaction is good for magnetism, but bad for superconductivity, bad for orbital order. So you start with a situation where originally system tries to develop spin density wave. But as I said, in the process it also changes, due to feedback effect, it changes sign of interaction in 2 other channels. So the question is, what happens? And it turns out that the result depends a little bit what is the value of the Fermi energy. But because you can only run RG between bandwidths and Fermi energy, you cannot run RG here because all equations become very different. But suppose I'm in a situation when Fermi energy is small and I reach instability within RG. So let's see what's going on. It turns out, I'll just very quickly finish with this. It turns out that the story is interesting, which has a lot of political implications. Namely, you will see the story. Namely, you start with a situation when spin density wave is the largest tendency. What I plot here is susceptibilities in different channels. When susceptibility diverges, it means that the system develops instability. So if I look only here, this is magnetic channel, this superconducting channel, this orbital channel. I can make this even larger. So this one is the #1 candidate. It runs, and it looks that the system will develop spin density wave. No. At some point, superconducting channel wins. At the end, orbital channel wins, which is kind of unusual stuff. And at the end of the day, for this particular case, you develop orbital order, but these are details and this important point. So what it means? It means why do we use the word political? Because read it this way. There is one interaction that was attractive, and the largest. It pushes up other interaction from repulsion to attraction, right? So the big boss is promoting a candidate. Then candidates are promoted. They conspire to stop the growth of the channels that promoted the interaction in the first place. And this is exactly what happens here. At the end of the day, magnetic susceptibility within RG does not diverge. Because negative feedback effect from 2 channels that become attractive, combined effect, basically stops the growth of spin density wave susceptibility. And this is a nice example of RG when one channel promotes the attraction in the other channels, and then other channels stop the growth in the channels that initially promote everything. So there are details about iron base, but probably you can stop RG if Fermi energy is larger, and then you get either spin density wave or you get superconductivity. But that was RG story. And again, this story has many details which I want to avoid, because otherwise it will be too much talk about details of iron, selenium, etc. But the whole story is this. This RG approach tells you one simple thing, that at the end of the day you start with attractive interaction in spin density wave channel. And you ask how it affects superconductivity and orbital physics. And you can start with repulsive interaction in the superconducting channel, superconductivity, and find out that because the system tends to develop spin density wave, it also converts repulsion into attraction. And you can stop there and say, okay, this means that I get attraction in superconducting channel, system has strong magnetic fluctuations, so let me move and study electron boson problem, which will be perfectly okay thing to do. Or you continue with RG, saying that I'm still at weak coupling, but I want to play the game with logarithms, etc. Of course, RG is not the full story, absolutely not. RG requires separation of scales. And if you don't have separation of scales, I mean, if this scale and bandwidths are comparable, then you can always only wave your hand and say, well, qualitatively it's okay, but on quantitatively, there's no quantitative reason to justify it. Nevertheless, so far, all functional RG, analytical RG, gave exactly the same pairing state as electron boson approaches or as general numerics like Monte Carlo given for a given model. Let me give you my conclusions. First of all, this is the main conclusion. There are examples where, by one reason or the other, and we can discuss in every particular case, we can discuss the reason, superconductivity most likely comes not from electron-phonon interaction, but from electron-electron. Which brings us to the issue, how can repulsive interaction give rise to superconductivity? General idea goes back to Kohn-Luttinger time, namely, details aside, that renormalization of interaction in the channels different from the pairing channel can change the sign of interaction in the particle-particle channel. This now viewed mostly as interaction mediated by either spin fluctuations or charge fluctuations. You get D-wave superconductivity in cuprates, you get S plus minus superconductivity in iron-based superconductors. One of advantages, and I don't know what successes of this application was D plus ID in doped graphene. You can also get S plus IS, S plus ID superconductivity. This all depends on the model. So there are a number of interesting features for superconductivity you can get. But in all cases, the story is that fluctuation in spin density wave channel enhance tendency superconductivity and orbital order. And the system self-generates attraction in both channels beyond the certain scale. So you start with repulsive interaction, system self-generate a scale below which the system, the interaction is attractive. And then these two guys, superconductivity and orbital order, conspire to kill the creator and to block spin density wave order. So I guess this, I would say thank you.
Very nice and clear talk, also for experimentalists, many times. And but if you are, for example, you consider the iron base superconductor, then
without the microphone.
You can, yeah,
okay.
sure.
And if you explicitly add some attractive interaction, electron photon, is there any feedback between the two mechanisms, so the repulsive, which gives rise to some attraction, and the real attractive interaction?
In some sense, yes. When you add electron-phonon interaction, you essentially add interaction most likely at small momentum transfer. Remember, there was term G1, which I treat as repulsion. And you start decreasing G1. And in this respect, so what you do Remember, G1 was a bad guy, the one that was against any superconductivity. You start decreasing this guy. And incidentally, the Dunn-Hailey idea of high TC in iron selenium film is exactly this, that electron-phonon interaction due to subtrade kill or reduce bad guy. Reduce interaction within a patch, within a pocket, while then interaction between pockets is much nicer amongst superconductivity. Yeah, so it's simple work, it's reduction of G1.
As a challenge and exercise for FRG,
Uh-huh.
and one which I've given to Dunhai as well. So can we tell from FRG whether strontium glutamate 214 should be P wave or D wave?
Ah, good question. First of all, FRG is, I'd say, I am in parquet RG. The difference is FRG is numerical method, parquet RG is analytical method. So, good question to which there is no answer at this moment. Because there is nobody did parquet RG so far, although it's doable.
Why not?
I'll tell you. It's not, so, okay, one, why not? Because, you know, I heard this buzz about strontium glutamate this year. So probably just means that wait a little bit and this will be done. On a more scientific way, RG works perfectly well when you have logarithms in this U. So for example, when you have small pockets, you have large distance. Here you have large pockets. So in this respect, RG will not be a rigorous procedure. Nevertheless, it's worth doing. And Ronnie Tamale did FRG, but at that time they mostly obtained P wave. They did obtain P wave. Now he says that they need to recalculate what they did before. So I'm already starting doing examples. So the answer is not given, but it's doable, but not rigorous. Because when you have large Fermi surfaces, you cannot place a gain of weight large logarithm.
When you have mentioned the first approach, you have said it's the doping remote insulator approach for superconductivity, but you say you pair itinerant fermions without including localization. So I guess that in the doping of remote insulator is where you include
Yes.
partially the mode physics. So why do you say without?